Good morning, students. So, in the last class, we have studied about the 555 timer, a stable multivibrator using 555 timer. So, in this class, we are going to study about the monostable multivibrator using 555 timer. So, now we are going to observe that. So, how our 555 timer is going to act as a monostable multivibrator. So, we have studied in our last class about a stable multivibrator using 555 timer and how to generate 50% duty cycle. So that is nothing but how to vary the time period of the square wave generated by the stable multivibrator. We have learned about that in a stable multivibrator. And whereas now we are going to discuss about monostable multivibrator. So in which the monostable multivibrator is a circuit which is going to produce a single pulse, and here in this monostable multivibrator, so we are giving external trigger signal. As we know that the monostable multivibrator is having a single stable state. So every multivibrator is having two states. So in this monostable, so monostable means only a single state is stable, whereas the other state is not a stable state. So that means the other state is going to depend upon the time period. So whenever we are going to apply a trigger signal, then whenever we are going to apply a trigger signal, then it is going to generate a pulse. So see here. So in this diagram, you can observe that the output stays at zero level until and unless we have applied a trigger. So when a trigger signal, that is a short duration pulse, waveform is applied, then the state is going to change. That is, the output is going to change from zero level to high level. So in this way, the monostable is going to have its high level for certain time period only. So you see here in this figure, we can observe that the time period is 2. So for time period 2 only, the state exists, that is unstable state, what we have discussed here. So as we know that, as we have discussed that, the multivibrator is having two states. So one is a stable state and another one is unstable state. In this monostable multivibrator, so it is having single stable state and another state is unstable state. So this unstable state remains for a certain time period only. So after trigger pulse is applied, so it stays for a time period T. So this time period T is going to depend upon the components which we have used in multivibrator. So mainly the time constant components. So like a resistor and capacitor. So this time period is going to depend upon the resistor and capacitor value. So now we are going to design a monostable multivibrator using our 555 timer. So how we are going to see now. So generally, where we are going to use this monostable multivibrator? Whenever we require a time delay, then we are going to consider this monostable multivibrator, as well as where there will be a possibility of dividing the frequency. So dividing the frequency, there we are going to use this monostable multivibrator. And also in pulse width modulation. So we have studied in analog communication subject that about this pulse width modulation techniques. So what is the pulse width modulation? Nothing but the width of the pulse is varied with respect to the amplitude of the message signal. So with respect to the changes in the amplitude of the message signal, the width of the pulse is varied. So this is also implemented with this monostable multivibrator only. Nothing but we are giving this message signal to the pin number 5 in our 35 IC. That is a control voltage, nothing but the control voltage. And it is also used as a switching element for a relay. So it is also used as a switching element for a relay. So relay is nothing but an electromagnetic component in which a control signal is given to that relay such that with the help of that control signal, it is going to switch on the devices which is connected to that relay. So that control signal can be applied with the help of this monostable multivibrator. These uh, these are the some of the applications of this monostable multivibrator. And now going to the monostable multivibrator. So this is the monostable multivibrator circuit using 555 IC. So see here, so coming to this diagram, as we have discussed a stable multivibrator, so the difference between, first we are going to observe the difference between a stable and monostable. So see here, the difference is, so there in a stable multivibrator, between 6 and 7 pins we have connected a resistor, and as well as we have shorted the 6th and 2nd pin in case of a stable multivibrator. Whereas a stable is self-generating multivibrator, so there is no need of input signal. Whereas monostable is having a single stable state. So because of that, for changing that stable state into quasi-stable state, we have to give an external signal to this monostable multivibrator. So for that, we have to give an input signal. So that input signal will be applied to a input that is the second pin. So the second pin is nothing but a trigger input. The second pin is nothing but the trigger input. So for this trigger input, we are giving the trigger signal for this circuit. Whereas the remaining circuit will be same as a stable multivibrator. You can see that 18 foot are shorted in a stable, as well as similarly we have shorted here in monostable also, because the fourth pin is the reset pin. It will we have to keep it always at high level, because if it is kept at low level it resets. So we are keeping it at high level. For keeping this at high level, we are making it connected to VCC. And 8 is the supply pin, so we have to give the supply to this pin. And then for charging and discharging of the capacitor, we are connecting a resistor to we are connecting a capacitor to a resistor to VCC. So here VCC, from VCC we are connecting a resistor, and then we are connecting a capacitor to the ground. So first pin is ground, as we know that the first pin will be ground, and fifth pin, this is the control voltage. Here whenever we are going to use this monostable as pulse width modulator, then we are giving input signal, the message signal to this fifth pin, or else it will be grounded with the help of a capacitor. Always we are making fifth pin to be grounded with the help of a capacitor. And then the sixth pin is a threshold pin, so which is shorted to the seventh pin, that is discharge pin. So now we are going to take output at the third pin. Output at the third pin. So coming to the operation of this multivibrator. So how this 555 is going to act as monostable multivibrator. So as we have discussed that whenever it will be, the monostable is going to remain in a stable state. Whenever the trigger pulse is applied, it goes to unstable state, that is quasi-stable state. And then this quasi-stable state remains for certain time period, and then it will be going to its stable state again. Again, this monostable is going to its stable state. So So that quasi-stable state is going to depend upon, and the time period of that quasi-stable state is going to depend upon the components which we have used here. So we have used here R1 and C1, that is time constant components R1 and C1. So this time period is going to depend upon R1 and C1. So we can see by adjusting this R1 and C1, we can adjust the time period of the output signal. So now we are going to observe the output, how output is going to obtain for this monostable multivibrator. This is the internal block diagram as we have discussed it in the last class. Last classes, that is in case of 555 timer explanation, that is a block diagram of 555 timer explanation, as well as in case of unstable multivibrator also we have explained about this block diagram. Now we are going to discuss about this monostable multivibrator using the 555 timer. What happens? So as we know that we are having the two potentials here. This is the potential divider, as we know that is a potential divider at which this node consists of 2 by 3 VCC and this node voltage consists of 1 by 3 VCC. So this comparator, as we know that this is a lower comparator. So whenever the trigger voltage is less than, that is the trigger voltage is less than this, if positive voltage, nothing but before the two op amps is going to act as comparators. Whenever the positive terminal, that is this positive terminal is having more voltage than negative terminal, then output will be 0. Whenever this negative terminal is having more voltage than positive terminal, then output will be at 1. So like that, these two comparators are going to operate. Whereas lower comparator, the positive terminal is fixed value, that is 1 by 3 VCC, and the upper comparator, the negative terminal is a fixed value, that is 2 by 3 VCC. And with the help of these two comparators and a flip-flop, we are going to decide the output of this monostable multivibrator. So what happens? Initially, we assume that there is no charge across the capacitor. That is, there is no charge across the capacitor, that is 0 volts. So output is also at 0 volts. Okay, output is also at 0 volts. So what happens? What happens to this circuit? When output is what happens to the circuit? So now let us consider about the operation of this circuit. So now we are going to observe that. So output is at 0 level. That means if output is 0, then what happens to the input of this output device? Here, output is 0, then what happens? So here we are having 1. Here we are having 1. So this 1 is applied to this transistor. So then what happens to this transistor? This transistor is going to on state. So when this transistor is on, then what happens? Whatever the charge across the capacitor is there will be discharged through this part to the ground. Will be discharged through this part. So in this way. So the discharge path is in this way. So discharge path is in this way. So the total voltage, whatever. So as we have assumed that the capacitor is not having any charge. So if there is any charge, that will be discharged through the transistor, to the ground. Okay. Then what happens next? So what happens next? Then we are going to apply the trigger signal. Now the output is at 0 level. So this is, let us assume this is 0 level. So now the output is at 0 level. So now we have applied a trigger. So at this instant, I have applied a trigger signal. So which is greater than my 1 by 3 VCC. So 1 by 3 VCC. So which is greater than 1 by 3 VCC. So then whenever I have applied a trigger signal, this output of this is going to 1. Output of this is going to 1 state. So output of this flip-flop is going to uh, this comparator is going to 1. And then output of this comparator is initially 0 because the voltage across this capacitor is 0, and then it is having highest voltage, the negative is having highest voltage, here negative is dominating, so the output is 1 here, it is 0. And when SG is 1, what happens? Q will be 1 and Q bar will be 0. Q bar will be 0. Then when Q bar is 0, then output is going to 1. So at this instant, my output is going to change its state from 0 level to high level. At this instant, my output is going to 0 level to high level, that is 1 level. So output is going to change its state to 1 level. So at this time instant, output is 0. Then this 0 is applied to the transistor. So 0 is applied to the transistor. Then what happens? Transistor is going to switch off. So now the transistor is off. The transistor is off. What happens then? So the capacitor is going to acquire the charge. Now the capacitor is going to acquire the charge through VCC. Now what happens? The capacitor is going to acquire the charge through VCC. So the capacitor is going to acquire the charge through VCC. So now the capacitor is going to charge. So from 0 volts to highest voltage. So I am showing you the waveform here with the different ink. So let us assume this is the capacitor voltage. So it is 0 and now the capacitor is going to charge. So it is going to charge. So up to where it is going to charge? Okay, up to where it is going to charge, that is when the capacitor acquires 2 by 3 VCC. When the capacitor is going to charge up to 2 by 3 VCC, then what happens? So when it reaches 2 by 3 VCC, okay, this comparator is going to change its state to 1. And this trigger pulse is a short duration pulse. So already this will goes to 0. So this will goes to 0. Then this is 1 and this is 0. What happens? So the flip-flop is going to reset. The flip-flop is going to reset. So reset means the output will be 0, Q will be 0 and Q bar will be 1. So when Q bar is 1, then what happens? So the transistor is on and the capacitor is going to discharge. Now the capacitor is going to discharge. The transistor is on and the capacitor is going to discharge. As there is no resistor in discharge path, then the transistor is going to discharge quickly to 0 level. So this is going to discharge. So as this is 1, the output is 0. So output is going to change its state from high level to 0. High level to 0 level. So in this way, this is the time period. So this is the time period T. So this charging time period is going to depend upon R1 and C1. This charging time period is going to depend upon R1 and C1. So this is how my triple side timer is going to act as a monostable multivibrator. Okay, monostable multivibrator. Okay, so this is what I have explained. So this is how. So when the trigger pulse is applied, then output is going to change its state from low level to high level. So at the same time, the capacitor is going to charge, acquire charge. So up to where this capacitor is going to charge? Up to VCC, up to VCC. So the final value the capacitor is going to charge is nothing but VCC. Is nothing but the VCC. Okay. Okay. Next one. So we are going to find the time period of this circuit. So how it is going to obtain the time period. So application, so it is going to use our frequency divider. So when we are giving trigger pulse, you can see, so here the frequency division is done in this you can observe the frequency division. Okay, here the time period t of the signal output is greater than the time period of the trigger pulse. Okay, whatever we are going to apply the trigger pulse, so that is less the two trigger pulses frequency division is possible by using this monostable multivibrator. So if you increase the frequency of the trigger signal, then frequency division, we can change the frequency division by 2, by 3, by 4, and it depends on our application, So next we can use, as we have discussed that we can use this monostabilizer pulse width modulator, nothing but here we are giving the message signal. So what is this? So if you give a message signal, at pin number 5, that is a control voltage, then what happens? This monostable multivibrator is going to act as a pulse width modulator. So simply you can design a pulse width modulator using this TTSI timer, which is going to use as a monostable multivibrator. Okay, this is how we are going to use monostable multivibrator. And here the time period of the signal is nothing but T is equal to 1.1 RC. So T is equal to 1.1 R1C1. So as we have discussed that what is this R1 and C1? So I have said that the time period of this monostable multivibrator is going to depend upon the resistor and capacitor values. So R1 and C1. So for that, for obtaining the derivation, so we are going to obtain the derivation for this. So for that, we are going to see here the derivation part. So in so this is how we are going to obtain the derivation part. Vc of t is equal to v naught into 1 minus e power minus t by rc. So for that, we know the formula. So in case of stable multivibrator, we have discussed about this formula. That is a capacitor charge across the capacitor can be given by Vc of t is equal to V final plus V initial minus V final into e power minus t by rc. So in the case in this case, we are going to discuss about that is V final is equal to VCC, and the V initial is equal to 0 volts. Okay, V initial is equal to 0 and V final is equal to VCC. So V final is VCC plus 0 minus VCC into e power minus t by RC. So whereas VC of t, what is this VC of t? So VC of t is equal to nothing but VC of t, which is equal to, so VC of t is equal to what? 2 by 3 VCC. 2 by 3 VCC. How this is obtained, I am going to observe. So see here. So up to where it has charged, that is 2 by 3 VCC. So we are going to write VC of t as 2 by 3 VCC. Okay, VC of t as 2 by 3 VCC. So 2 by 3 VCC is equal to VCC into 1 minus e power. So at at T1, so this is this we are going to consider it as T1. Okay, T1 at T1. So this we are going to consider T1. At T1, it is equal to 2 by 3 VCC. Okay, so T1 2 by 3 VCC is equal to VCC into 1 minus e power minus T1 by RC. Okay. So now by solving this equation, so 1 by 3 is equal to, so what happens here? So both sides VCC is there, so we are going to cancel this VCC. So 2 by 3 is equal to, so what happens? 1 by 3. So by solving this, we are going to get e power t1 by rc. ln of 1 by 3 is equal to e power minus t1 by rc. t1 is equal to rc ln of 3. So whereas we are going to take a natural logarithmic on both sides. T1 is equal to RC ln of 3, T1 is equal to 1 by 1.1 RC. So we're going to obtain T1 is equal to 1.1 RC. So whereas we know that RC value is going to be R1 and C1, where R is equal to R1 and C is equal to C1. C is equal to C1. Okay. So next, so this is how we are going to obtain the monostable multivibrator. Okay, this is the time period. So how we have obtained the time period, we have observed it, we have observed here, and observe here. Thank you, students.